Center of Astronomy and Astrophysics in India and Pennsylvania State University, USA. She is a member of LIGO Scientific Collaboration and the LISA Consortium. Her research mostly focused on detection and the parameter estimation of the gravitational wave signals coming from mostly from the binary systems composed of the neutron stars and black holes. Thank you.
Okay, now let's over to Dr. Anuradha. Yeah.
Okay, I can start, I guess. First of all, thank you so much for inviting me to present this talk. I think it has been long. I have never given any public talk during the pandemic. Means before that I gave one, but this is really a good experience for me to start giving public lectures as well. So let's get started. As the topic of my talk you see is gravitational wave, a new window on the universe. You might have heard of gravitational waves or not, but I will confirm that you may learn something about gravitational wave after this talk. So I will start with something familiar, what we know. This is Sun, the closest star to us, and this is also the lifeline of our solar system. Sun is very massive. It has mass of around 2 times 10 to the power 30 kilogram, and the radius is almost 7 lakh kilometer. It's so big. So Sun currently is burning nuclear fuel at its center, which is giving us energy in electromagnetic radiation, and that is what we are observing at Earth. So this so Sun, just like human beings, also was born some time back, and it is currently at its midlife, and it may die sometime. So what happens to Sun, say after so many billion years later? So the life cycle of Sun is such that it was born some 4.5 billion years ago, and as I said, it is currently it's in midlife. So suppose if humans live 60 years, and so Sun is about 30 or 35 years of his life. So Sun will keep burning its nuclear fuel at the center, keep giving us the energy, and after about 5 billion years later, when it run out of its fuel, it will become a red giant, and it will then collapse and form a planetary nebula, and then at the end form a white dwarf. So at the end of the life cycle of Sun, we will get a white dwarf. So white dwarf is a dead star, which I'll talk about more about that. So this is about Sun, and Sun is an ordinary star because we have more massive stars than Sun in our galaxy, in our universe. So what happens to those stars which are more massive than Sun? So if you have a star which has its mass around the mass of the Sun, then eventually it becomes a white dwarf. But if you have star, that means you can star which is 4 to 8 times massive than Sun, then it will eventually live its life, and eventually it will become a neutron star. And then if the star was massive, 8 times more massive than the Sun, then it will collapse to form a black hole. So this is what happens when different sizes of stars die at the end, and we get different types of dead stars: white dwarf, neutron stars, and black holes. And these are the dead stars which I study. So let me tell you more about these dead stars. White dwarf, the typical radius of white dwarfs are 5,000 to 10,000 kilometers. So basically, you can compare the sizes of white dwarf with Earth. They have similar sizes, but the difference is that white dwarfs are much more massive than our Earth. They have mass around less than 1.4 solar mass or something. So that means that if you have the mass, equal to the sun, but you are putting that mass together in the size of Earth, then that object has to be very massive. So have to very dense. So white dwarfs are dense stars. If I compare them with neutron stars, they are even more denser stars, because the typical radius of neutron stars are 10 to 15 kilometer, and the masses are 1.4 times the mass of the sun. So now you can imagine that you have 1.5 times more massive star than our sun, but it is now occupying only a region of 10 kilometer or 15 kilometers. So it is even more denser. So black holes are actually at the extreme end. So black holes are regions in the space-time where all the mass, whatever mass black hole has, it is all pointed to a point. So black holes are the most dense stars in our universe. Since they are denser, the gravitational field around them will be so strong. It will be so strong that nothing can escape black hole, not even light. And hence the name black hole, because we cannot see black hole through light. So these are the properties of white dwarf, neutron stars, and black hole. These are stars. These are death stars. So all the stars in our universe actually love to be in pair or in groups, I think just like humans. So it is very common that if you have a star, it mostly will have a companion star, and the two stars will orbit around each other around their common center of mass. They can orbit around each other on a circular orbit or in an elliptical orbit, and so on. So since these dead stars are also stars, they will also be in binary systems, and then we will have binary of neutron stars and neutron stars together, neutron stars with black holes, and black holes with black holes. So we have these different kinds of binary systems. And what is special about these binary systems is that they emit gravitational waves. They emit strong gravitational waves, which we can detect. So this is the topic of my research, and this is what I do for my living. I heard a ping. Is there any question at this moment?
Hi, Anuradha. We can actually answer these questions at the end if that is okay with you.
Okay. Yeah. Sure. Yeah. But just interrupt me if you have something in the middle. Okay.
Okay. Sure.
So let's start talking about gravitational wave now. And it all started with Newton. Newton, we know, who gave all the laws of motion, laws of gravitation, and because of him, we are studying physics today. So Newton gave a law of gravitation, which says that if you have two masses of mass m1 and m2, and they are at a distance of r from each other, there will be a force of gravity acting between these two masses, which will be given as g times m1 times m2 divided by r square. So Newton's theory of gravity was very successful for over 200 years. It explained every motion on Earth and almost every motion in our solar system. But there was some problem with Newton's theory, because Newton described the gravity as a force which acts instantaneously between the masses. So, and Newton might not himself know that how gravity works. So the problem is with the instantaneity of this force, because if the two masses are at certain distance, as long as they become at a distance r, they will start experiencing the force. And is it really possible? Because how one mass will know that there is another mass around it? Let's take an example of our solar system. So all the planets in the solar system revolve around sun, right? So suppose, and this is because of the gravitational force between the planets and the sun. So suppose the sun suddenly disappears, just in a click, it disappears. So which means that the force between the sun and other planets will also disappear. So will this information reach all the planets simultaneously at the same time? The answer is no, because the Mercury will know that Sun has disappeared, then the Venus, then Earth, and then Mars, and so on. So it takes time to travel the information from one place to other place, and that was the problem with Newton's gravity, because he described gravity as instantaneous force. So for this, Einstein came to rescue. So Einstein first gave his special theory of relativity in 1905, where he gave two postulates. He says that all the laws of physics are same in all inertial frame of reference, and inertial frame of reference are those which travel with constant speed. And the second postulate was that the speed of light is same, which is 3 times 10 to the power 8 kilometer per 3 times 10 to the power 8 meter per second in all inertial frames. So Newton also described the notion of four-dimensional space-time, and he says that we are all living in four-dimensional space-time, where three dimensions are the spatial dimension, and the fourth one is the time dimension. Time is not absolute, it is different for different observers. So that is the main difference between Newton's gravity and Einstein's description of this theory, what he gave. But Einstein's special theory of relativity was applied to only special cases, as the name says, because what are those special cases? It was applicable to only inertial frames and flat space-time. So if you want to study motions in non-inertial frames which are accelerating, or you want to study motion in curved space-time, then Newton's special theory of relativity was not applicable. So then he gave a general theory of relativity in 1916, where Newton described gravity as a curvature of space-time rather than a force. So now Einstein said that we all are living in a four-dimensional fabric of space-time, where matter actually produces the curvature in this space-time, and the curvature is actually telling the matter how to move in that space-time. So let me give you an example here. So if you have a massive object, it is sitting around. So because of its mass, the fabric of space-time, you can imagine that fabric as a sheet of cloth. And what happens if you put a big ball in that sheet of cloth, that the sheet curves, right? So something is the same thing happen in our space-time. If some very massive object is there, it will produce a curvature in that space-time, and any other smaller body will just near that massive body will just follow the curved path. And you may see that it's the same motion what Newton described, because Newton said that there is a force and the smaller body should revolve around the bigger body. So so Einstein's description was different in explaining the same motion. So in our solar system, Sun is very, very massive than other planets. So Sun has its curvature, and all the the smaller planets are just following the curve created by Sun. And that is, the motion can also be described by Einstein's theory of gravity. So here the space-time on the left is telling how the curvature is actually telling how the masses should move. And if there is a mass and it is moving, there will be curvature in space-time. And we also so if there is a mass which is moving and there is a curvature in space-time, there are also ripples in space-time, and those ripples are actually gravitational wave. So here is an example of two black holes which are orbiting around each other. Black holes are massive objects, they are producing curvature, but as they are moving, they are also producing ripples in this space-time, and those ripples are gravitational waves. So this is how we describe gravitational waves. And if we can measure these ripples, we will know that the gravitational waves exist. So you can also imagine, like, if you have a still pond, a pond with still water, and if you drop a stone, what will happen? There will be ripples around the stone, right? And if somebody is far from that point, and they can also see that ripple, and they will know that somebody has thrown a stone in that pond. So if something happening out there in our universe, which are producing gravitational wave, which are ripples in the fabric of space-time, they can travel and reach us. And so that if we have the strong detector, we can detect them. So gravitational waves, now we know, are ripples in space-time. They are predictions of Einstein's general theory of relativity. They are waves, so that they will have amplitude and wavelength and frequency, but they are not electromagnetic wave. They are different than electromagnetic waves. Electromagnetic waves are produced by the acceleration of charged particles. Similar to that, gravitational waves are produced by the acceleration of masses. And just like electromagnetic waves have different polarization states, gravitational waves have two polarization states. One is cross polarization state, another is plus polarization state. What it means is that if you have a ring of free particle and gravitational waves which has only cross polarization, it is passing through that ring of particles. So these particles will start oscillating such that the ring makes the cross shape. And if the passing gravitational waves passing gravitational wave has only plus polarization, then the ring will expand and squeeze in plus manner. So so it is actually possible to observe then if we can measure this change in the shape of these objects through which gravitational waves are passing. So we can actually define the amplitude of gravitational wave by strain amplitude, which is just delta L by L. Delta L is the change in the length of that object through which the gravitational wave is passing, and L is the original length. So this is how we can, if we measure this strain, that means we have measured the amplitude of gravitational wave. That means we have detected gravitational waves. So let me tell you some more distinction between electromagnetic waves and gravitational waves. As we know that electromagnetic forces are strong forces, gravity is a weak force. It is easy to detect electromagnetic radiation or electromagnetic waves because we just have to collect the photons, but they can be easily blocked. On the other hand, it is hard to detect gravity because it is gravitational waves, because gravity is a weak force. And but the good thing about it that it can pass anything from the universe being undisturbed. So we can actually then see gravitational wave far from the universe without being disturbed on the way. We use electromagnetic waves to construct images of celestial object, just like we are making images of any astronomical objects. So we use photons to make that. So you can think of gravitational waves as a way to listen to those astronomical objects. So now you have eyes through electromagnetic radiation to see the universe. Now with gravitational waves, you have ears to listen to the electromagnetic to the universe. And it might surprise you that only about 10% of the matter in our universe can be observed through electromagnetic radiation. So if we really want to see the rest of the 90% of our universe, we need to rely on gravitational waves, because gravitational waves are fundamentally different way of observing our universe. So it's both, we require both. We need electromagnetic observation as well as gravitational wave observation to have a complete picture of our universe. So this is the animation I'm showing. This is a vastly exaggerated animation to show that what happens if gravitational waves are passing through Earth. So as I showed you, if gravitational waves are passing, the object should squeeze and expand. So this is something similar happened to Earth, but this is vastly exaggerated. This is nothing like that happens in reality, because gravitational waves are gravitational waves produce very tiny effect, because even if they are passing through Earth, we would not know most of the time, because their effects are so small to feel anything, or maybe to measure anything. So I'll give you an example here. So suppose you have two masses, 1,000 kilogram of masses. Basically, these are big masses. I think yeah. So 1,000 kilogram is a big mass. Suppose you have two such masses 10 meters apart, and they are rotating with a frequency of 10 hertz. So the gravitational wave they produce, because these masses are accelerating, right? So by definition, any accelerating mass should produce gravitational waves. So if these masses are accelerating at a frequency of 10 hertz, they should be producing gravitational waves at 20 hertz, and the amplitude of the produced gravitational wave will be something like 10 to the power minus 43. So you have a strain amplitude of 10 to the power minus 43, and this is a very, very small number. If you want to measure this strain, that means if you have a 1 meter stick, to measure this strain, you have to measure the change in the length of that stick of the order of 10 to the power minus 42 meters. I cannot imagine if there will be any operators on Earth which can measure a distance of the order of 10 to the power minus 42 meters. So that's the reason anything which produces gravitational wave on our Earth is so tiny that it is impossible to detect those gravitational waves, because the strain amplitude is so small. But if we look out in the outer space, if there are two neutron stars are in a binary system and they are orbiting around each other with a period of 1 second, they will also produce gravitational waves, but the strain amplitude of that produced gravitational wave will be of the order of 10 to the power minus 22. It is still small, but it is much better than the previous example. It's like 20 order of magnitude larger than that. So what this strain amplitude of 10 to the power minus 22 means, if you have 1 kilometer of length, and then you want to measure the strain, the change in the length will be of the order of 10 to the power minus 19 meter. It is still a small distance to measure, which is about 1,000th time of the diameter of a proton. But it is not impossible, because we have done it. We have the technology to measure such small distance on Earth. So if we want to detect gravitational waves, we have to look for the violent events in our universe. And because the larger the masses, the more violent the event will be, and the more strong the gravitation will be, so that we can detect them. So that's the reason we are looking for black hole binaries, neutron star binaries, and so on, so that they can, because they produce gravitational wave which we can detect. Otherwise, it is almost impossible to see from other sources. So now since I said that it is possible to detect gravitational wave, how do we detect them? So the principle behind the detector, making a detector to detect gravitational wave, is based on Michelson Interferometer. I'm sure that you must have heard or learn about Michelson-Morley experiment in your physics courses. So it is similar principle. It's the same principle. You have two mirrors, and you send a laser light to those two mirrors, and the light gets reflected back to a third mirror. And if the two lights cancel out each other, then you won't see any photon and the photon in the detector. But if they don't cancel out each other properly, then you will see a light. So that is what it is happening. The the reflected lights from the other mirror in an L-shaped Michelson interferometer. They have the same length. If the length is not changed, the two reflecting lights should cancel each other, and there shouldn't be any photon in the diode here. But if for some reason the length of the two arms changes, and the reason being passing gravitational wave, because we know that if gravitational wave pass, they change the length of objects, right? So if the gravitational wave is passing through this detector, they will change the length of the two arms, and so that the two reflecting lights cannot cancel out each other, and we will see a light in the photodiode. So this is the technique we use in detecting gravitational wave. But as you know that we need to measure these are very tiny effects to measure. So that we need to measure the strain of 10 to the power minus 22. We have to have very big detectors, and we build it. Actually, we have two LIGO detectors in USA. These were built they were started building some 30 years ago, and the arm of these two L-shaped interferometer is 4 kilometer. Each arm is 4 kilometer. These are twin detector. They are almost identical. Why we want identical two detectors? First of all, is that it's always better to have more detectors, because we can then also cancel, we can also rule out noise sources and other things. So it is always better to have more than one detector to observe the same thing. And these are so big arm because we want to measure very small strain amplitudes. And just to give you an idea what is a 4 kilometer arm look like, it will be the distance from the IIT Hyderabad main campus to the Sangareddy crossing. So the one arm of this detector is that distance. So these were built in USA, the twin detectors. And this is a picture of inside one of the, so at the end of these L-shaped detector, we have mirrors, right? Because through which the light will be reflected. And this is the picture of inside near one of the mirrors. So using those two detectors in USA, after 30 years of preparation, in 2015, 14 September 2015, we actually did observe gravitational wave, and it was almost 100 years after the prediction from Einstein. The signal we detected was coming from two black holes colliding into each other, and they were 1.4 billion light year away from us. And behind this discovery, which was a milestone discovery, there was a group of 1,000 scientists all over the world which contributed to this effort, and there were actually researchers from India as well. So the two black holes which merged, which orbit and merged at the end, they form a bigger black hole, and this is to give you an idea of how big those black holes were. So the black holes were 36 solar mass and 30 solar mass. So one is 36 times mass of the sun, another was 30 times mass of the sun, and they were orbiting, and when they merge, they form a bigger black hole of mass 65 times massive than sun. And the sizes you see in the map, that will be the typical size of these black holes. So you can see that 65 times mass of the sun is being compressed in a region which is equal to the size of a state in India. So you can see that how dense that object must be. So that the signal we detected, the gravitational wave signal we detected, actually lies in audio band, and we know that the audio band means the frequency which humans can listen, from 20 hertz to 20,000 hertz. So these gravitational waves are waves, they have frequency. So, and their frequency also lies in the audio band, and actually we can listen those gravitational waves. So this is what you are listening, the chirping signal. Chirping means the two black holes are orbiting around each other, and at the end they are just merged. and there is no gravitational wave afterwards. So this was a milestone discovery. It was a threefold discovery because that was the first direct detection of gravitational wave, because before that we had only detected gravitational wave indirectly, and that this was the first observation of black hole binaries. We have never detected black holes in a binary system before, and this was the first direct observation of black holes, because whatever we had before this discovery was from electromagnetic observation, and from electromagnetic observations we had only black hole candidates. We didn't say that we have detected black holes. We said we have black hole candidates because we were not sure the things we have detected were actually black holes or not. So this was truly a breakthrough discovery, which was threefold, and because of that discovery, actually, the 2017 Nobel Prize in Physics was awarded to these three scientists: Ray Weiss, Barry Barish, and Kip Thorne. These were Ray Weiss was the person who proposed the LIGO detectors to be built to search for these gravitational waves, and Barry Barish was the person who helped building those and maintaining those detectors. And Kip Thorne actually gave the theory behind how we can build models which we can use in our data analysis to make sure that we have detected gravitational waves. So these three people were awarded the Nobel Prize in Physics in 2017. And as I said before, this was not just the job of three people. It was the job of 100 scientists all over the world. And this is the picture which was taken in 2016. And there were 35 scientists from 9 Indian institutes who contributed to this first detection. And I was also part of that team back in 2017 when I was a postdoctoral fellow at IUCAA. So we have 2 detectors in US, but it's an international effort. Now we have also other detectors in other part of the world. For example, we have GEO 600 and Virgo detector in Europe. We have almost ready to take data detector in Japan named as Kagra, and we have a planned detector to be built in India named as LIGO-India. So as I said before, the more the detectors we have, it is better for our observation, because there are many other complications. I don't want to go into the details, but the thumb rule is that more detectors are better. So let me give you a zoom in picture of how it looks like for the detector in Virgo. So this is the 3 kilo arm length L-shaped interferometer in Pisa, Italy. It is already taking data, and because of this detector, actually we had the first observation of neutron star binaries back in 2017. This is a picture of the detector we have that is built underground in Japan. It's called Kagra. It has 3 kilometer arm length, and it is underground. It is cryogenic. That means it is at the very small temperature, so that we can get rid of photon noise and other noises, etc. And the one which will be built in India is LIGO-India, which will be 4 kilometer arm length. And for this detector, we already have in principle approval from the government of India back in 2016. And the current status is that 99% of the land acquisition is completed. We are formally in construction phase, and environmental clearance is also received, and so on. So it is, as it says, that it is formally is in construction phase. So maybe in 8 to 10 years, we will have a detector, a gravitational wave detector on Indian soil, which will join the network to detect more gravitational waves. So if you want to learn more about what is happening in India in regarding gravitational waves, please check out the link I have given at the bottom. So this, since 2015, since the first detection of gravitational waves, in 6 years, in 6 years, we have now 90 more sources. So this is the picture where we are showing all the binary systems, including binary black holes, neutron star black hole binaries, or neutron star binaries, which we have detected through gravitational waves. So you can see that it is just in 6 years we have 90 sources. And as if you are comparing what we have detected through electromagnetic radiation, the bottom line is showing you what we have detected in electromagnetic radiation in last 40 years. So this is so amazing to see that in last 40 years we have detected only handful of black hole candidates and neutron stars, but in just 6 years we have detected so many binary systems and black holes and neutron stars from gravitational wave. So it is truly remarkable, because as I said, we need both types of observation to have a complete picture of our universe. And because of this gravitational wave observation, we came to know that there is a mass gap actually between 2 solar mass to 5 solar mass, because you see that we have a dearth of objects in this range. Is it real, or is it just a selection bias effect, or what? So this is kind of, it gives you an open question, open problem, that what is happening at this mass range. So with new discoveries, actually you have more questions to solve. So as I also said that gravitational waves emit signals in audio band, and this is the typical gravitational wave signal look like in time domain. So basically the two black holes are orbiting around each other, so you have a sinusoidal signal, and as they come closer and closer, the amplitude is increasing and they merge, and then after the merging they form a big black hole, and after some time there is no gravitational wave. So this is the typical gravitational wave signals look like in time domain. But if you listen carefully, do you see a blip? Do you hear a blip?
No, Anuradha, I think we don't. Yes.
So that sound is the merging of two black holes. So that is what we call the symphony of the universe, because these signals are
Once again, ma'am, please.
Sorry, one more time.
Once again, ma'am, please. Sound.
Okay.
I can't hear.
Do you hear? Okay, I'll give you
Yes,
another
ma'am.
chance. So this was very short signal and hence very short sound. Now, if you have a larger signal, going through many cycles for many seconds, you will have a continuous sound, and then at the end you see the blip thing. That is where the two neutron stars are merging and forming another compact object. So I'll play it again. I hope you heard that. So if you want to have more such audio to listen, you can actually visit this this website. This is the Open Science Data Center from LIGO and Virgo collaboration, where we have all data available and all sorts of animation available. So you can also check out if you are interested in that. So
Thank you, ma'am.
yeah, so what we can learn about gravitational? First of all, it was a big deal discovering a gravitational wave. But what does it tell us about our universe? So, of course, we can learn about the 90% of our universe, because 90% of our universe cannot be seen through electromagnetic radiation, first of all. And what else we can learn is that we can learn about the fundamental physics. For example, we can learn about gravity at extreme condition. So the gravity or the gravitational field around neutron stars, black holes are so strong, we have no idea what is happening there. And through gravitational wave, actually we can then learn about gravity at extreme condition. Similarly, we can learn about nuclear equation of states, because neutron stars are made up of neutrons, and when they are in a binary system, when they merge, they get crushed to each other, and we have heavy elements emission. So by observing neutron star binaries, actually we can learn about the nuclear physics and nuclear equation of states. We can learn about astrophysics of objects. For example, we can see how black hole binaries are formed, what makes two black holes to come together, form a binary, orbit, merge. What are the physics? What is the physics behind that? And what makes two black holes, two spins, and precession? So there are many other things we can learn in astrophysics through gravitational waves. We can learn about cosmology using gravitational wave. And as I said, that gravitational waves can travel large distances without being affected by things at their on their way, because they are weak forces. They are very lightly interacting with anything on the way. So we can see gravitational wave from very far in the universe, and then learn about the physics at the cosmological distance. And actually, we can also see gravitational waves which were produced just after the formation of our universe, just after the Big Bang. So these are called early universe gravitational waves, which we can also see. And this is not all possible with electromagnetic wave, because with electromagnetic radiation, we can only see at the CMB, which is a cosmic microwave background. Beyond that, we have no idea what is happening. And gravitational waves are the only mean which can go beyond that and tell us what was happening before that time. And of course, there will be unexpected sources or phenomena, because since so far in the last 400 years of astronomy, since Galileo, who made the first telescope, it has been 400 years ago, and so far we have seen the universe through electromagnetic radiation, and it has just been 6 years we have started seeing or listening our universe through gravitational waves. So we will expect, as our detectors become more sensitive and more powerful, we will see some unexpected sources we never heard of, or maybe learn about some unknown phenomena, because with different tools we can have different discoveries. So let me tell you a bit about the future of gravitational wave astronomy. We are talking about the future because we have just been in the business for 6 years. There is a long way to go, but we can look ahead and see what we expect in next 15 to 30 years. So we are actually trying to build more powerful, more sensitive detectors than we have, because with these detectors, which are called Einstein telescope and cosmic explorer, which will be Earth-based system, we will build them on Earth. They will be so powerful that they can see each of the black hole in our universe. They will see all the black holes of our universe. So the Einstein telescope, which will be built in Europe, it will have arm length of 10 kilometers. So if you remember LIGO detectors, the current LIGO detectors have their L-shaped arm length of 4 kilometer. Now it will be 10 kilometer, and it will be again underground cryogenic. The one cosmic explorer will be built in USA, whose length will be 40 kilometer. It will be 10 times more larger than the current LIGO detectors. So larger the arm, more small strains we can measure, or more further we can see the gravitational waves. We have also funding for a space-based detector, LISA. It's called Laser Interferometer Space Antenna. It will be we already have the funding. It will fly sometimes in 2035 or something, maybe in 15 years. So it will be a triangle shaped interferometer, where the length of one triangle is actually 1.5 million kilometer. So these are big detectors. Why we need them? Because we want to see more of our universe through gravitational waves. So that we have a long way to go, and we are waiting for these detectors to come up to have more and more detections for gravitational waves. So this is the plan for us in gravitational wave from next 15 to 30 years. And if you guys are interested, or if you get motivated in any way, you also have, and if you want to do something with gravitational wave, there is a lot of opportunity in India through LIGO-India and Indigo Consortium. So we need to build LIGO-India. We need experts in quantum metrology, laser physics, vacuum technology, optical engineering, and control systems, because these will be required to build the detector. And then we have to have people who help with the physics or the theory of gravitational waves. We still need accurate models for gravitational waves. We need our electromagnetic partners through X-ray observation, radio observation, gamma ray observation, and neutron observation, because gravitational wave alone is not sufficient. We need both of them, electromagnetic and gravitational wave together, so that we can have a complete picture of our universe. And of course, there'll be opportunities for outreach and higher education. So this is kind of all is linked to the LIGO-India project. It is a mega project from India, and you can contact people in Ayuka or me if you are more interested in learning about any of these things. So with this, I'll stop, and thank you for your attention, and I'll be happy to have any questions.
Thank you, Dr. Anuradha. Such a nice presentation and so much of information about the gravitational wave, also particularly this LIGO-India project. Thank you. And we have a few questions. So I'll just read one by one, and then we can answer. So Muhammad Shamid Hussain, he asked, do black holes have infinitely large density, or is it finite but very huge?
We don't have density defined for black holes, so you can say that it's infinite. Yes, it's not an object. It's kind of if you call a finite size object when you can define its dimensions, right? And then knowing its dimension and mass, you can compute the density. But there is no finite size of black hole, so there is no finite density for black hole.
Excuse me, ma'am, please. Excuse me, ma'am, please.
I'm sorry.
What is the meaning of infinite in physics?
Yeah, so we don't know anything actually about black hole, what is inside a black hole. So what we see is the apparent horizon of the black hole, so which is kind of the 3 kilometer radius from its center. So what is from the 0 kilometer to 3 kilometer, we have no idea. So again, it's an open problem. We don't know what is happening. So what we can say about black hole is only what we see at the apparent horizon, which is kind of a region far from the center, where the electromagnetic, if there is an accretion disk, we can observe through electromagnetic radiation and so on. So we only see black hole from the outer radius of from the apparent horizon. So as I said, infinite density, it's not a finite size, so there is no density defined to it.
Okay. Ambika has a question. How are photons affected by the gravitational field of black holes if they are massless?
Can you repeat that question?
How are photons affected by the gravitational field of black holes if they are massless?
If they are massless, so okay, so from special theory of relativity, we have that term the booster term. Okay, I'm also want to revise my special theory of relativity. So actually, photon do follow the path, the curved path created by the black hole. So they are just following the geodesic. It's not about the mass. It's like if you have anything, and the geodesic means you have the curved path, and there are lines around it. Just like if you have a ball, and if you draw lines on that, these are called geodesics. So the photons are just following that geodesics, and that is, you say, they are being affected by the mass of the black hole. So it is nothing to do with the mass of the photon, I guess.
Yeah, okay. Saurabh has a question. Are there something called white holes like black holes?
There are mathematical models for white holes. These are mathematical models we don't know if they really exist in practice. Just like wormholes. Yeah, so wormholes are just mathematical models.
And then can hypothetically we see the objects falling onto the black hole, or due to the relativity it will take forever to fall into the black hole?
Yeah, of course. Yeah, through the relativity, first of all, if something is falling in the black hole, they will be ripped apart because the tides are so strong there. But yeah, as I said, we don't know anything what is happening inside the black hole. So yeah, the time will be so slow around black hole and inside maybe. So it will be just relativistic effects you will be seeing.
Okay. Dipankar Nath has a question. How pure are polarizations created by various sources? Do we see only one type of polarization, or do we see mixed type?
No, yeah. So that is a good question, because I forgot to tell when I was describing the polarization. So the picture I showed where the rings were oscillating in plus or cross manner, that is just an example. But in practice, whatever gravitational waves will be observing, that will be a mixture of the two. So it will be only very special configuration or a very special orientation of the source with respect to detector, where you will see only plus polarization or cross polarization. But in general, it will be a mixture you will be seeing at the detector.
Okay. Muhammad has one more question. So, if 90% of the universe is made of not real matter, so like dark matter, dark energy, so is it possible to detect them using gravitational waves?
Yes, actually, there are being studies using gravitational waves to detect dark matter, dark energy. For example, dark matter. So there are so many dark matter candidates, and so there is, and also depending upon, there are so many models. So actually, we can test those models using gravitational wave. One example is that there one model which says that there are dark matter particles at the center of a neutron star, and what happens is that when these dark matter particles scatter through the neutron star, they accumulate at the center, and after some time, these neutron stars will collapse to form a black hole. So if that happens, that means that we will have more black holes at the cost of neutron stars. So maybe comparing the merger rate or the rates of neutron stars and black holes, we can constrain the size or the mass of these dark matter particles. So yeah, so it is possible, and people are working on that. It is in its early stage, I would say, but it is possible to do that.
Okay, sure. Ambika has one more question. So if these strain amplitudes, they are very small, like 10 to the power minus 22, and it's very difficult to detect, then how can we be sure that the instrument what has picked up is actually a gravitational wave, not some other kind of signals like an error measurements or so?
Yeah, so that is again a good question. So how do we make sure that what we have detected is not noise but gravitational wave? So that is the reason we have at least 2 detectors to detect the same gravitational wave, because if there was a noise in one detector, the noise in the other detector will be uncorrelated to that. So it will be impossible that the same noise will be in both the detectors. So we can then, if we have 2 detectors and some gravitational wave is coming, then what we can do is that we can cross correlate the data from one detector to other, and then see, because the noise will be uncorrelated, they will go away, and what you will left with is the gravitational wave. That is one thing. But even in a scenario when something happens in our ionosphere, or in that there'll be same noise in both the detectors, which is also highly unlikely, but suppose that happens. So, but there are actually techniques in data analysis where we can distinguish a noise in the data as compared to gravitational waves. So we have tools to distinguish noise from the data in that case. And on top of that, we actually also calibrate our detectors. So before starting the observation, we calibrate our detectors. That means if we are seeing something in the photodiode, we set that threshold that this is without gravitational wave, and then if something is coming, that photodiode will read something different, and then we will know that there is some signal coming to the detector. So yeah, so there are all sorts of techniques to make sure that we don't have a false alarm for gravitational waves.
Okay, thanks. Shubhajit has a question. Whether these waves, GW waves, are they propagate through space, or they will decay with the distance, like with the propagations?
Yeah, so that is again lots of good questions. So in GR, in general theory of relativity, gravitational wave travel without any disturbance. So there is no friction between of the space time which can make gravitational wave decay. But there are theories of gravity. These are called non-GR theories. So in those theories, there are some friction terms involved, and that makes gravitational waves to decay. But again, in general theory of relativity, from Einstein, there is no friction. So gravitational waves just propagate freely.
Okay, and also he has one more question. Like space-time fabric is like an imaginary concept. Is it possible to detect disturbance? Yes, actually, I think we are detecting lots of them right now. Yeah. Okay, Ambika has one more question. So black hole mergers are stronger. The signals due to the black hole mergers are stronger than the neutron star. Is it right?
Yeah. So the more mass you have, the heavy the stars are, the more strong the gravitational wave will be, because the amplitude of gravitational waves is basically proportional to the mass of the binary.
Okay, yeah. I think the similar questions Mr. Amit also has. How do you detect like the waves signals are from a neutron star or neutron star black hole or black hole merger? Does the amplitude give such information?
So how we distinguish the signals from the 3 sources? Is that the question?
Yes, that is.
Yeah, actually, that is also a very nice question, because there is a distinct signature in the gravitational wave signal. So for example, if I go back, yeah, so here, so these two signals, right? So one is coming from, on the left, it is coming from two black holes merging, and on the right, it is coming from two neutron stars merging. And clearly we see them, they are different to our eyes. One is shorter signal and other is very long signal. So at least just by the masses of the two merging objects, you can say that they are black holes or not. There, okay? But suppose we have black holes whose mass is similar to neutron star, then it will be very difficult to distinguish. So there is one parameter we use to distinguish called tidal deformability parameter. So what happens is that if you have a neutron star and a black hole, and that neutron star is orbiting around it, around the black hole, and as the neutron star comes closer and closer to the black hole, because of the tidal effects, the neutron star kind of become disrupted, and it become disrupted, and then it has all the metals and all the matter which is going around, and that will have a distinct signature in this gravitational wave. So and actually we can measure that distinct signature when we do the data analysis. So it is possible to distinguish between neutron star binaries and black hole binaries.
Okay. One more question, whether there is any reason to place the detector underground rather than on the surface?
Yeah, there are many reasons. For example, there are so many noise sources. So there is one gravity noise, there is seismic noise, there is photon noise, there are quantum noise, there are so many noise sources, and we have to deal with all those noises when we are building detectors. So by making the detector underground and cryogenic, so by making the cryogenic, we can get rid of photon noise and maybe quantum noise, and by making it underground, we can get rid of, I think, gravity noise and some of the seismic noise. So the reason to build them is reduce the noise in the data. Yeah.
Oh, sure. And one more interesting question: which one is faster, electromagnetic waves or gravitational waves?
In general theory of relativity, they travel with same distance.
Same density.
But in other theories of gravity, as I told that one example I gave with the friction, there are many other theories of gravity which says that they will travel different speeds. But in general theory of relativity proposed by Einstein, electromagnetic waves and gravitational wave travel with the speed of light.
Okay. Poppy has one question: is gravitational waves depends on the speed of accelerated masses?
Yes, yes. So accelerated masses, as you see here in this figure on the left, so you get a sinusoidal signal in the beginning, and then what you see is that then the amplitude is increasing, and then it is decreasing, and then that keep decreasing, and then after that there is a zero signal, right? I'm talking about the figure on the left. So this is actually telling you the speed of the accelerating masses. So if you're going from left to right, the speed of the masses is increasing. So if you have larger the speed, you will have larger the amplitude. So that is the relationship.
Okay. Yeah, so many questions, Anuradha. So I think if Mohammed has one more question.
Yeah, sure. It's getting late for you guys here. I'm just starting my day.
As you said, ma'am, according to general relativity, there is no decay of friction for gravitational wave, but there are some. Just 1 second. Okay. There are some of the other theories according to which the waves decay. What exactly happens in reality? Do you experiment friction or do they not?
Yeah, so in that case, then gravitational waves and electromagnetic waves will travel with different speeds.
Yeah, okay.
Because gravitational wave is affected by some friction, and if electromagnetic radiation is not affected by the same friction, then they will travel with different speeds.
Okay, okay. And Ambika has one more doubt, like the one in one of the slides where you played these two signals blips, for one for neutron star and one for black hole. So it seems to us like the neutron star sounds, the volume amplitude sounds more than the black hole. So I guess that is just like a audio effect, right?
No, I think I don't know. I didn't understand. So you're saying that black hole signal is louder than the neutron star signal?
She seems that it's other way around. So neutron stars seem louder than black hole.
Yeah, it may be. I think it's yeah, it could be the sound effect.
Yeah,
Because the louder the sound, the louder the gravitational wave should be. So yeah, I think it's just the audio file effect here.
And also, I guess, Anuradha, I have one question regarding this. So let's say you have like two neutron stars, like close to, let's say, 1.8 solar mass, and they are merging. And you have two black holes, like which is, let's say, 2.5 to 3 solar mass, they are merging. I mean, do you can really distinguish at that boundary, like whether this two neutron star or two black hole when the masses are very comparative?
So that at that case, it will be bit difficult to distinguish. I think I mentioned very briefly that if we have black hole binaries whose masses are similar to neutron star binaries, then it become a bit difficult. And I think with the current detectors, we cannot distinguish with them because our detectors currently are not sensitive enough to measure that tidal deformability parameter I was talking about. So the way to see the difference is actually to see the post-merger signal. When I say post-merger, if you look at the figure on the left, like after the highest amplitude, where the two objects merge and then it is decaying, right? So that is the signal for black hole, two black holes merging. I don't have a figure here, but on the right, here I'm showing just at the highest amplitude, but there is nothing after the highest amplitude, right, on the right figure. But there will be something, a complicated signal, which will not be the same as the one on the left, and that is called post-merger signal. So basically, actually just comparing or analyzing the post-merger part of the signal, we can distinguish because those should be different. But the problem is that the current detectors are not sensitive enough because post-merger signals are very small, right? The amplitude you see are even smaller than the initial amplitudes. So since these amplitudes are so small, we need stronger detectors or maybe more sensitive detectors to measure that part, and that's why we need these third generation detectors, Einstein telescope and cosmic explorer, because they will actually we will be able to analyze the post-merger part of the signal properly with these detectors. So yeah, currently it is very difficult.
Okay. And Abhijit has a question like, can we determine the distance to those black holes? Those are marching from the signals.
Yeah, we can, because the amplitude actually will tell you the information from the amplitude and the phase of the signal actually tells you the distance and the masses together. So you see that this sinusoidal thing, I'm telling you, these will be they will have different structure for different black hole masses. The distance just basically scale up and down the amplitude, but the signature you're getting in the sinusoids are different for different masses. So basically, by measuring the phase and amplitude together of a signal, we can then measure the masses and distance from the source.
Okay, and one last question. So does this orientations, probably the detector you was talking about, does it matter for the detection of the events?
Yes, it does. It very well matter. I don't have a picture here. I should have. So there are actually not. We say that our detectors are omnidirectional. Omnidirectional means it can detect signals from all the directions, but it is not true because of the location of these detectors on Earth, and there is also Earth rotating every day. So there are blind spots on the celestial sphere where the detectors cannot see anything. So it depends, like where in the sky your signal is coming from. If it is coming from the blind spot, then your detector cannot see it. So that's the reason we should have all these detectors all over the world, so that the area of the blind spots can be reduced. So more the detectors, less will be the blind spots.
Ma'am?
Mm-hmm.
Ma'am, I have a doubt from the slides.
Yeah.
Ma'am, there was a curve or something in the dark theme. Can you explain what was on the X and Y axis?
This one?
Yes, ma'am.
Yeah.
Yes, ma'am.
This is kind of confusing. So on x-axis, on y-axis, we have masses in solar mass unit. So 1 solar mass, 2 solar mass, 5 solar mass, and so on. X-axis has no meaning. It's just we just arranged the black holes in a nice butterfly fashion. X-axis doesn't have any meaning. It's just the y-axis, which tells you the masses of these black holes and neutron stars.
And ma'am, the gap that you were talking about, what was that?
Yeah, so before the discovery of gravitational waves, direct discovery of the gravitational wave in 2015, whatever we had, the knowledge about these objects, black holes and neutron stars, was from electromagnetic observations, right? X-ray observations. So before 2015, from X-ray observations, we saw that there was no black hole between 2 solar mass to 5 solar mass. So people, like scientists, were puzzled what it is. Is it a selection bias effect? Because smaller the black hole, it will be more difficult to detect it. Because in theory, black hole can have any size. There is no restriction on a black hole to not have mass in any range. I mean, a black hole can have mass continuously in all the range. So before 2015, in X-ray observation, we didn't have black holes from 2 to 5 solar mass. People said that it's a selection bias effect, because X-ray, we cannot see X-ray radiation from sources which have black holes in 2 to 5 solar mass. But with gravitational waves, we are now actually start seeing some of them. But since again we are in our early stages, it has been only 6 years, we have not populated this gap very properly. So maybe we have to wait and see if this gap will be populated by gravitational wave observation. But currently, this is it's an open question, because we don't really know. It's a gap because we cannot explain that gap. A black hole can have any mass, but what it is, it's a selection bias effect, because smaller black holes are harder to detect.
Okay, so Mr. Amit has one question. Space-based detector will reduce the number of blind spot?
So yes, that is true. But space-based detectors actually are also looking at very different spectrum. So the ground-based detectors actually will detect gravitational waves in audio frequency range from 1 hertz. Audio means, I mean, in kilohertz regime, 1 hertz, say 1 hertz to 5,000 hertz. And this LISA will actually detect the gravitational waves in millihertz regime. So 10 to the power minus 3 to 0.1 hertz. So they'll be seeing different sources actually. So LISA will be seeing mergers of supermassive black holes, which ground-based detectors cannot see. So it's like you can think of like electromagnetic. We have different types of electromagnetic telescopes. In IR, we have radio, we have X-ray. Why? Because we want to see sources who are emitting in these at these wavelengths. So similarly, we need different types of detectors to see or to listen to gravitational wave sources which are emitting gravitational wave in different frequencies.
Okay, I think that's all from the so many questions, and I guess like the students, they are still asking like whether I should share your email ID with them in case if they have any questions or doubts they can ask.
Yeah, sure, for sure. I'll be happy to answer your questions.
Okay,
If
thank
I know that.
yeah. Thank you, Dr. Anuradha, for such a nice, wonderful talk. And then we have so much of information about the GW wave, and probably I will share her email ID. And then if you have any further doubts and questions, anything even regarding developing your career or anything on this gravitational website, you can contact her. She will help you definitely.
Yeah, for sure. Thank you for having me.
Yeah, thank you very much. Bye.
Bye.